Okay, in the last video, we did a Taylor polynomial for the sine of x, and this time we're going to do the same thing for the cosine of x. Now we'll make the same assumptions that we did last time. We've got a cosine function. It will be centered at x equals 0, and we want to find the Taylor polynomial and also the general term. And then after we find the polynomial, we'll look at it graphically to see what the thing looks like. So it's almost going to be a repeat of the Taylor polynomial for the sine. And as a matter of fact, I would suggest if you haven't done it, go ahead and before you watch this video, watch the video on Taylor polynomial for sine. And it'll give you a little bit of an idea of where this one comes from. Okay, to begin with, anytime you want to do a Taylor polynomial, the first thing to do is to actually write the formula down. So let's take a look at the formula on this. And if you go to your books, you should find this. So this is what you'll find, and it's in two forms. If it happens to be centered at any point, you have what's called a Taylor polynomial, and it's in the form x minus c. However, there's a special case called a Maclaurin polynomial centered at x equals 0. And they're actually exactly the same thing. The only difference is the Maclaurin is centered at 0. A regular Taylor polynomial could be centered anywhere. Now, if you centered it at 0, that means that c is equal to 0. So if you look up at this formula, you would have x minus 0. So the x minus c squared would just turn into x squared. Makes it a little bit simpler. So in our problem, it's centered at 0, and even though the question said find a Taylor polynomial, actually we'll use the Maclaurin polynomial. But again, keep in mind, all Maclaurin is a special case of Taylor. So we're going to use this formula right here as we run through it. So let's go ahead and start the whole process. Again, the very first thing to do always, whenever you're working with Taylor polynomials, is go ahead and write the formula down, because really it's just a matter of getting the right things in the right spot in the formula. So the formula looks like this, and I went ahead and color-coded it a little bit. All the stuff in blue involves derivative information. All the stuff in red involves factorial, and then in black is just the power terms on this. So the process will look something like this. Now, the first thing you've got to do is to find all these derivatives. So we'll just go ahead and put a little step over here. So the very first step is going to be to find the derivatives. So we'll put find the derivatives, and that's going to be the first step. Now, once we found the derivatives, the next thing I have to do is to evaluate the derivatives at x equals 0. And I would suggest you write these side by side just to make sure you don't miss any of them. So we'll put here evaluate the derivatives. So evaluate the derivatives at x is equal to 0. So those are going to be our two steps to come up with the blue part of the formula. Now to start with, what you're going to need, let's go through it step by step here. You'll need the original function, then you're going to need the first derivative, the second derivative, and however many you need. So we'll go over here, and the very first thing will be just go ahead and put f of x. So f of x, the original function, I think I'm going to do this in blue. So I'll make it be f of x is equal to, and the original function is the cosine of x. And now it's just a matter of building up a list of the different derivatives. Now, as far as how far you go, it's up to you, like we talked about in that first video on the sine. I'm actually going to go out to 6 terms just because I want to show some special things on the graphs. But you can go out to, sometimes the problem will specify something like find a 4th degree Taylor polynomial. In that case, you'd go out to 4. But in our case, we'll go ahead and actually put 6 derivatives here. And again, just a kind of a slow process, so just be nice and patient, and you will eventually get there. So f prime of x, the first derivative, that's going to be this term right here. And just the derivative of the cosine is the negative of the sine. And then you just keep continuing on. You've got f prime prime, the second derivative. And the derivative of the negative sign, you got the negative, the derivative of the sine is the cosine. So this will become the negative of the cosine of x. Let's get the third derivative. And it would just be the derivative of this thing. Well, you've got the negative. Then the derivative of the cosine is the negative of the sine. 2 negatives make a positive, and so that'll turn into the sine of x. then we'll go to the fourth derivative. Now again, just on the notation, after 3 primes, most people switch to parentheses 4. So what that notation means, that is the fourth derivative. And that's going to be, the derivative of the sine is the cosine. And we'll get 2 more. So the fifth derivative, and this is of x. So the fifth derivative of x. And again, the derivative of the cosine is the negative of the sine. And I'm going to go ahead and get a sixth one just to help us with some graphing stuff later on. So the sixth derivative would be, and again, the derivative of the negative of the sine would be the negative of the cosine. So what that does, this gives you the first 6 derivatives. Now, I would suggest you always go straight across here, and I like to put them horizontally just to make sure I don't skip anything. So basically, I'm going to take this and move it straight across to here. And now I want to take these derivatives and evaluate them at x equals 0. So first of all, I've got the cosine. The original function would be the cosine of 0, and the cosine of 0 is 1. Then I'd have the negative of the sine of 0. Now again, the sine of 0 is 0, so the negative would still be 0. Then I've got the negative of the cosine of 0. So just everywhere you've got an x, plug in a 0. Cosine of 0 is 1, so that's going to give me a negative 1. Then I've got the sine of 0. So this one's going to be sine of 0. And again, I'm still just coming straight across on these like this. Sine of 0 is 0. Then I've got the cosine. So the cosine of 0 is 1. Then I've got the negative of the sine of 0. And the negative of the sine of 0 is 0, so if you make it negative, it's still 0. And then finally, you've got the negative of the cosine of 0. And the cosine of 0 is 1. To take the negative of it, you get a negative 1. So what happens now, in this column, you've got the blue part of these coefficients up here. So what I would suggest you do is to rewrite this thing, and I'll take this formula here. So I'm going to go ahead and just grab a copy of this thing and move it down and write it down one more time here just to make sure I don't miss anything when I fill it in. So I'll do this. I'm going to go ahead and take this and move it from here, and I'll move it right down to here. So I'm just going to rewrite it one more time to give me a place to start. So it'll look like that. Okay, now it's just a matter of filling these things in. So let's just go across and start filling stuff in here. First of all, I want P sub n, so the polynomial is going to be equal to, and now it's just a matter of getting each thing out of this list over here. So you want the original function evaluated at 0. Well, that's this one right here. So the original function of the cosine evaluated at 0, that's your first coefficient, or first term. So this is going to be 1. Then you've got plus. Then you want the first derivative at 0. Well, that's 0. So it's going to be 0 times x. So 0 times x. Then you want the second derivative evaluated at 0. Well, second derivative would be negative 1. So this is going to be negative 1 times x squared. And then don't forget, though, the factorial. Easy thing to forget, do factorial. Then I'm going to have plus. Now I need the third derivative. Well, the third derivative is 0. So this is going to be 0 times x cubed divided by 3 factorial. Then plus, now I need the fourth derivative. So this is going to be, the fourth derivative would be 1. So I'm going to have 1 times x to the fourth divided by 4 factorial. Then I'll get the fifth term. So the fifth derivative would be 0. So this one's going to be 0 times x to the fifth divided by 5 factorial. And finally, let's go ahead and put the sixth one on here. The sixth one would be negative 1. So I've got a negative 1 times x to the sixth divided by 6 factorial. And then for a while, we'll put plus, and it's going to go out, and it'll stop after a certain number of terms, after n terms, but we'll pick that up in just a second. So now you've got it to this. But you can actually simplify it a little bit, so let's scoot this down just a little. And remember, some of these terms are going to disappear. So anything that's multiplied by 0 goes away. So 0 times x, that term right there will disappear. 0 times, this has got a 0 coefficient, that term will disappear. 0 coefficient, that term is going to disappear. So any term that has a 0 coefficient is going to go away. So now we'll rewrite it one more time. So this is going to be p sub n of x is equal to, and just keep the terms that are remaining. So I've got a 1. Now this becomes negative x squared divided by 2 factorial. The next term, it switches back to a positive. So positive x to the fourth divided by 4 factorial. And then here's a negative again, negative x to the sixth divided by 6 factorial. And then it just goes on. Now eventually it'll come to a stop. Now remember, the original problem said find the general terms. Let's take this and just move it back up here again. But the original problem said find the Taylor polynomial, which we've got now, but we also need the general term, which is what that last term would be. In other words, it's this term right here. So you've got the specific terms, but you need to know in terms of n, what is this thing going to look like? So let's go ahead and put that in there. So it goes all the way down to here. Then I'm going to have a plus. Now to get this, we'll just look at the series here. And you've done this before where you change a series into its general terms. Now the first thing to notice, it alternates. It goes plus, minus, plus, minus, plus, minus. So you're going to need a switch in there to switch it from plus or minus. And the way to get that is negative 1 to the n. Now you should have done this several times back in previous work. So you're going to need a negative 1 to the n. It starts with a positive, so that since we go from n equals 0, that'll take care of the alternating part of it. Then you're going to have x raised to some power. Now this, I think, helps a little bit too. If you come along and do this right here, this is going to be the first term. N is equal to 1. Or pardon me, it starts at 0. N is equal to 0. This would be n is equal to 1. This is going to be n is equal to 2. This is going to be n is equal to 3. And then so on. You'll put 4, 5, 6. So if you get out here, you're now at n at the end. So to figure out what the exponent on this is, just looking at this numerator, if you're at the third term and it winds up being a 6, you've actually doubled it. So you're just going to take twice n. I think we'll do it in black just to stay consistent here. So that's going to be twice n. Now, for the factorial on the bottom, you've got the same thing. 2 gets doubled to 4, 3 gets doubled to 6, which tells you that this would be, whatever the term is, you just double it, and that gives you your factorial. So what this is, this right here is the general term. So you've now got the general term. So that's going to be the general term. So you've got the polynomial and you've got the general term, and that's going to be the polynomial, Taylor polynomial for a cosine. Now one last thing you might want to do, and I'll do that on this problem, is sometimes especially when you're graphing these things, it's helpful to go ahead and change these factorials into a number. So even though this is a good answer, let's also rewrite it like this. We'll write it as p sub n of x. And you can also see it in this form. It's got a 1. Then you've got minus, you've got x squared. And 2 factorial is 2 plus x to the fourth. Then you've got 4 factorial is 24. Then you've got minus x to the sixth, and 6 factorial is 720. So these numbers get pretty big in a hurry. Plus, and you can go all the way out to this nth term up here. So we'll stop at some nth term over here. So anyway, when you're graphing them, sometimes this is a better form. So you can have it in factorial form, or you can expand the factorials and get it like this. So that's the answer. Now, just like we did in the sine video, let's take a look at the graph and try to get a feel for what this thing really looks like. So what I'm going to do is scoot this down, and we just want to concentrate on that right there. And we'll take a look at the term-by-term contributions on this thing when you work with a graph. So I'm going to scoot this up. We've got a graph to look at, and we'll stop it, say, about right here. That looks pretty good. Okay, now let's look at contributions of these things and what the effect is as you go through this. So first of all, let's do this. I think I'll go back to this again and just suppose we were just going to look at this first term right here. So I want to know, and don't consider any of these terms at all. Remember, you get to have maybe a second degree polynomial or a fourth degree polynomial. You get to choose how many terms you want. So let's assume we did this. Suppose I wanted to find, estimate the cosine, but only using one term. So this would be like having the graph y is equal to 1. So if we graph that, it's going to look very similar to this. We'll go back to here. All it's going to be is a horizontal line that goes right through 1. Now, the blue graph is the cosine. This pink graph is the graph y is equal to 1. Now, first thing you should notice is that right away it does a really bad choice. So let's just kind of zoom into this area right here and notice. As soon as you start moving away from the center, it's things centered at 0, the pink line and the blue line begin to separate. So what this means is letting y equal to 1 is really a terrible choice. It begins to separate almost immediately. So a 0 order polynomial here won't do you any good at all. So basically, this first term does you no good whatsoever. So let's try this. Let's go back to this, and let's go to 2 terms. So we'll put a little, just a extra. That was a very bad choice. So suppose you went out to 2 terms. How accurate would it be? So you want to find the cosine, and the question now is, what can you put in there? How far out can you go and still get an accurate answer? Well, again, let's look at our things here. So what I want to do is go to the second order one, which would be this one, and let's put that graph on there. Okay, if we back away, here's what it looks like. So this pink one was the 0 order. Now, if you have a second degree, you've got a thing that looks like this, and notice that the orange graph, the second degree graph, seems to agree with the cosine graph for a longer period of time. So let's see how far we can investigate this one. So if we zoom in right in this area, now the question is, how far out can you go before the orange graph begins to separate from the blue graph? And just looking at it, it looks to me like, and we can actually kind of zoom in here a little closer, it looks like, I'm going to guess somewhere around 0.5. So if you wanted a reasonably accurate estimate of the cosine, you could go out to about 0.4 or 0.5. Let's just suppose we went to 0.5. We'll push it. So using a second order polynomial, you can get a fairly accurate answer out to about 0.5. So the next question is this: what happens if you added another term? So let's add a x to the 4th term. Now the question is, how far out can you go and get a fairly accurate answer here? Well, let's take a look at our graph. Again, we'll go back to here, and I'll put the 4th order one up. Okay, so this light blue graph here represents the polynomial with 3 terms out to x to the 4th. And notice it extends the range that you can model the graph. So we'll move things up just a little bit and scoot it over to here. And what I'm going to do is zoom in just a little bit right in here and try to figure out, where does this light blue one separate? So if we go right into here, now notice the pink graph separated almost immediately. This orange graph gave you a pretty good model up to about 0.5, then it began to separate. But if you look at this light blue graph, it seems to be fairly accurate, and we'll get in a little bit closer here. You just want to know, where does this light blue graph begin to separate from the dark blue cosine graph? And just looking at it, I'm going to guess you could get out to about 1.2 and still get a pretty accurate answer. We can zoom in just a little bit there. Notice they're in close agreement right here. So if you wanted to find an estimate of the cosine, you can go out to about 1.2 radians and get a pretty accurate answer. Beyond 1.2, these 2 graphs begin to separate and the accuracy answer falls off a little bit. So then let's try adding another term. And again, remember, the more terms you add, generally the more accurate the answer is going to be. So this time, let's go from here, and we'll go all the way across to here, and we'll pick up 6 terms on this thing. So now how far can you go out and still have this one be accurate? Well, again, let's go back and look at our graph. We'll go back to here, and let's go ahead and add the 6th degree. And if we put it on there, it's going to look like this. So now this new red graph here is out to x to the 6th. And all it does, it extends the range that the model conforms to the cosine. So again, all the action seems to take place right down in here. So let's zoom in and see what we've got here. We'll go in and see how far out the red one goes before it begins to separate. Now looking at it, it looks to me like here's the red graph, and you're curious, where does the red graph begin to separate from the blue cosine graph? And it seems to be fairly accurate, almost out to about 2. I'm going to go ahead and say put a 2 here. By 2.2, it looks like it's beginning to separate. So at 2, it seems to be hanging in there pretty well. So what this means, I can go out to approximately 2.0. Now, beyond 2, the red graph begins to separate from the blue graph, and I would need another polynomial. So if you wanted a more accurate answer, you may have to go out to plus x to the 8th. But the idea is that they just, each one, as you add terms, you improve the accuracy of the answer. And then finally, this is kind of interesting to do. Let's go in here. Notice, if you're in, the closer you are to the center, which is at 0, all of them are fairly accurate, except for the pink one, of course. So let's do this. Let's just zoom in right here and see how they actually look here. So I'm going to go in here, and I'm going to go very close to 0.5. So when x is equal to 0.5. Now notice, right now, if you're pretty far out, all 3 of them, the pink one's bad, but the other 3 look pretty good. So let's just keep zooming in. So as I zoom in, I get into about here, and now eventually at 0.5, the orange graph begins to separate. That's this second order one right here. And we'll just keep zooming in. So the orange graph begins to separate. Now at this point, there's actually 3 graphs still left in here. You've got the original cosine graph plus the 4th one and the 6th one. So we'll keep zooming in. And if you zoom in, you begin to see them separate. And the fact that you can't see those last 3, they're all together, tells you that the 4th order, the 6th order are both really good models because they haven't started separating out yet. So I'll keep zooming in, and then finally you begin to see a little separation here. That's the 4th order one beginning to separate out. So I go in, so this blue graph right here is the 4th order one. Now as far as the accuracy goes, look at this right here. Let's go across to here. At this point, you've got about 0.877. Here's 0.8, this is 0.8776, 0.877. So what this tells you is that the blue graph, the 4th order graph, is actually pretty accurate to about 3 decimal places. But let's keep zooming in. Now as you zoom in, first of all, it looks like this red graph is just all by itself, but there's actually an x to the 6th term in here. All it means is x to the 6th is doing an excellent job of modeling the cosine. So we keep going in. Now at some point, that red graph is going to separate from the blue graph. And again, notice you're in very tight right now, but let's keep going in until there's a distinct separation. So if you keep going in, finally you begin to see it. So if you get in close enough, the blue graph is the cosine graph. The red graph is this 6th degree polynomial. And notice they just begin to separate, but the question is, they're fairly close together, but how accurate is it? We'll look right over here. You've got 0.87758 and 0.87758. So at this point, this red graph is accurate to about 5 decimal places, which is extremely accurate. Now what we'll do, let's go ahead and zoom back out, and you can kind of watch each graph will sort of blend back into the original as we go through here. So as I back out, there goes the 6th order one. This blue graph, here comes the 4th order one, and it'll blend in. And you keep going out. This orange graph is the 2nd order one. If you keep backing out, it'll blend in. And then you just keep backing out, and eventually you can see the whole thing. So again, a long way out, all the graphs look pretty good except for the pink one. And it's not until you zoom in that you begin to see the differences. But the thing to take away from this again is the more terms that you pick, generally the more accurate the answer is. And then also notice the closer you are to the center, the more accurate the answer is. So as you move away from the center, the graphs all begin to separate. If you're in close to the center, there's a chance all of them will work pretty well. So second order works okay, fourth order works okay, sixth order works okay. But as you go further out, you're going to fall back on higher terms. And then one last thing to show you on this before we leave is just a little bit of a memory aid. Let's do this. Is in the last video we did sine, this video we did cosine. We came up with two different Taylor polynomials, and they look like this. Okay, one final thing before we leave here. This is a memory aid to help you with remembering the Taylor polynomials for sine and cosine. Now, when we did the sine one, this was the polynomial we came up with. When we did the cosine one just now, here's the polynomial you came up with here. Now, to help you remember these, you might remember what the graphs look like. This is roughly a graph of the sine. This is roughly a graph of the cosine. Now, if you remember back from your algebra and pre-calculus days, even and odd functions. Now, let's start with an even function. What an even function is, if you take any point on this side, they're symmetric about the y-axis. So take a point here, go to the same distance on the other side, there's a point over here. Now, if that's the case, that's called even. So that is an even function. Now, another way you might remember those is that if you have an even function, all the exponents are even. And think of this as being x to the 0, which is even. So a cosine is an even function. So if you're looking for a way to remember these, just remember that since a cosine is an even function, all these exponents are even. And what an odd function is symmetric about the origin. What that means is take any point here, go directly from there through the origin, go the same distance on the other side, and there's a point right there. Pick this point. Go directly through the origin, same distance on the other side, there's a point right there. So if that's the case, it's an odd function. Now notice, in the sine, all the exponents are odd. So odd, odd, odd. Think of this as being to the first power, which is also odd. So if you can remember, the sine is an odd function, which should help you remember that the exponents on the Taylor polynomial for sine has odd exponents. The exponents for the Taylor polynomial on the cosine have even. So there's one final little memory. So anyway, there's an example of the Taylor polynomial for the cosine and a little bit of a look at the graph to show you how they operate.